These are the Chapter 14 Notes 4 on Linear Regression t-test. You may recall the last couple of days we have spent constructing these linear regression t-intervals. The equation that we've worked with the last few days has looked like this. B plus or minus t star times SEB, the standard error of the slope. Now in this equation we have two values. We have this statistic, which is B, that's our slope of our line, our sample slope. And then we have this stuff that's after the plus or minus, that is your margin of error. So when we're constructing our linear regression t-interval, we are making an estimate of the slope, and when we attach the margin of error, this interval that we get makes a prediction about what the actual slope would be if we had the entire population of points. So confidence intervals are used to predict the slope of the population data. Today we're going to set up something called a linear regression t-test. Now, a linear regression t-test is going to answer a question for us. And usually the question has to deal with maybe one of two different things. One, if the relationship between x and y is truly linear, and whether or not the slope of this line is equal to 0. So when you read a question that involves using a linear regression t-test, a lot of times the question will be worded one of those two ways. Is there a linear relationship between x and y, or is the slope between x and y equal to 0? When you set up a linear regression t-test, we will have 4 steps. And just like we had with our chi-square test or our one proportion or one sample t and z test, we're going to start off with some hypotheses. H sub O and H sub A. Because we want to see if there's a linear relation or whether the slope is 0 or not, we're going to talk about the null hypothesis being there being no relationship, or you can say that beta is actually equal to 0. Beta is our abbreviation for the population slope. On the other hand, the alternative hypothesis is that our slope of our population is either less than or greater than or just plain old not equal to 0. Now, most of the time, this is going to be what your null hypothesis and alternative hypothesis will look like for this type of test. Usually the number at the end is 0. I have seen one case, however, where this value is not equal to 0. So although I'm going to say it's usually 0, and most of the times you can typically just kind of write this value, occasionally we might consider some other number, like 1 for example. Besides writing the hypotheses for our first step, we're also going to identify the name of the procedure. The name of this procedure is a linear regression t-test. However, sometimes it's also called a t-test for slope. I will typically use linear regression t-test because your graphing calculator identifies it as such. If you go to stat tests, a lot of people's calculators will have this linear regression t-test, so I'll usually call it that. However, it is also correct if you want to call this, so I'm going to say AKA, also known as a t-test for slope. That is another way of calling the name of this procedure correctly. Once you have identified the hypotheses and the procedure, we can move on to our conditions. And the same two conditions that we used for our linear regression t-interval we're going to use here. The first condition is that your observations are independent. That means we have no repeated observations of the same data point. Usually that's pretty easy to show. And then for conditions 2, 3, and 4, instead of listing those different conditions about the true relationship is linear, the points are normally distributed about the least squares regression line, the standard deviation of the points about the regression line is the same everywhere. Again, you can make your little residual plot and talk about the residual plot shows random scatter. Therefore, it is not unreasonable to assume that the other conditions for inference are met. So I'm going to start the phrase here, and you can finish it with the same wording that we had talked about the other day. When you carry out the procedure, this is a t-test, so we are going to calculate t. And the formula for t is pretty simple. We're going to take little b, the slope of the sample regression data, minus beta sub 0, the value we used for beta in our null hypothesis. Most of the time you can use 0 here. And then we're going to divide by our friend SEB that we talked about the other day. the standard error of the slope. The degrees of freedom is still equal to n minus 2, and you can use the linear regression t-test to find the p-value. When you conclude this problem, similar to what we did before, the first thing you want to talk about is the value of the p-value. So since the p-value is less than or greater than 0.05, we reject the null hypothesis or fail to reject the null hypothesis. That's your first sentence. And then you're going to have the statement about there is significant evidence or there is not significant evidence that. How does the problem conclude? Well, the problem concludes by saying there is significant evidence or not significant evidence that there is a positive or negative association between whatever x and y are. And when you're doing this t-test for slope, we're trying to see if there's a relation. If the slope is anything other than 0, that means it's either going positive or negative. And typically the question will state which of these things you're actually testing about. Again, in context, we're going to use x and y here. So that's all there is to it. It doesn't take up a lot of space, and it should be pretty easy to work through. Let's flip to the back side of your worksheet and set up an example of this type. Okay, so let's work through the example on the back side of your worksheet. We're going to use data from problem 14.1 on page 786. And down here toward the bottom of my screen here, I actually have a little screenshot underneath the calculator of the femur and humerus data. And the question reads, is there significant evidence of a positive association between femur length and humerus length? We want to figure out, as the femur length increases, does the same thing happen with the humerus length? Seems logical that it should. Let's actually test it out. We're going to start with your null hypothesis first. And the null hypothesis in this problem is that beta is equal to 0. This essentially means there is no association. If beta equals 0, no relationship, no association. The alternative hypothesis, if we're talking about a positive association, we're going to use the inequality that would denote a positive association, which would be greater than 0. The name of this test is a linear regression t-test, and at this point we are done with step 1. Step 2, check conditions. We have 5 observations here. I think it's very reasonable to assume that these are independent observations. So we can say independent observations were taken. To check our next condition, what we're going to have to do is we're going to have to go to residual plot in our calculator and see what the residual plot looks like. So the first thing we want to do is we want to enter in those 5 numbers into your calculator. I'm going to enter those in list 1 and list 2 by going to stat edit. And we're going to enter in these numbers, the 38, 56, 59, 64, and 74 for x. And then the y values are 41, 63, 70, 72, and 84 for y. Upon entering these numbers in to make a residual plot, you need to do a few steps. First of all, you need to figure out what line these points are going to be close to. We need to actually calculate the residuals. So to do that, we need to know what line we're working with. So of course, we go to stat calc number 8, linreg, and this gives us our linear regression equation. In our equation, you'll notice that there is a value for b that you can see right here. We'll eventually be plugging this in step number 3. However, right now we're working on a residual plot, so once you do linreg, we're going to go back to your list menu. We're going to highlight list 3, and we're going to access the residual list, which you can find by hitting second stat. If you scroll down this names column far enough, one of the items should say resid, R-E-S-I-D. Hit enter a few times, and you should have the same number of points appearing here. Now, if you ever end up with a different number of points for list 3 compared to list 1 and list 2, go back, redo the linreg step, and it should calculate the correct residuals for you. Finally, we're going to get a residual plot by going to your stat plot, second y equals. We're going to turn our first plot on, making sure that we're graphing list 1 and list 3, and using the scatter plot tool. Finally, hit zoom 9, and this will give you a nice picture of your residual plot. You should notice on your residual plot a horizontal line right here. Be sure to include the horizontal line on your picture. There aren't a lot of points here, but I think you can clearly see that we have random scatter of a residual plot. So we will say in step 2 that the residual plot shows random scatter, therefore it's not unreasonable to assume the other conditions for inference are met. Now that we have our conditions finished up, let's talk about carrying out the procedure here. To calculate t, what we're going to do is we're going to take little b, the slope of our sample data, minus beta sub 0, which is based off of the slope identified in the null hypothesis, divided by SEB. We can find lowercase b on your calculator by going to Stat, Calc, number 8, Linear Regression. And the number we're going to use is the slope value that you see here on the calculator screen. Officially, that's equal to 1.196900115. And we'll try not to round that if possible. Minus beta sub 0 comes from the null hypothesis beta. Beta in the null hypothesis is equal to 0. Divided by SEB. So here's where we use our calculator program. We're going to run the SEB program. Assuming you've entered your numbers in list 1 and list 2, you enter the sample size, which is 5, and your calculator tells you that SEB in this problem is equal to 0.075085435. Now, if you actually divide these numbers on your calculator, if you take the 1.196900115 number minus 0, which is the same thing, and divide it by 0.075085435, your calculator spits out an answer of 15.94. Your degrees of freedom, of course, in this problem are equal to n minus 2. 5 data points minus 2 is equal to 3. We also want to talk about the p-value here as well. So to calculate the p-value, we've got a couple options. The first option is to go to Stat, Test, choose the Linear Regression t-test option if you have that, and hit Enter. You'll be prompted to enter in your X list and Y list, which we put list 1 and list 2. We're going to pick the direction that the alternative hypothesis is pointing to in our problem. Ours is a greater than problem, so we'll make sure the greater than option is selected. Make sure the frequency says 1, and we'll go down to Calculate. And what you'll see on this screen is a t-score that we got, 15.94, our degrees of freedom, which do equal 3, and a very small p-value in this problem, 2.684 times 10 to the negative 4th power. That is one way of calculating the p-value. You can also access the p-value by going to second vars, your distribution menu. You can choose TCDF, and you're going to be prompted to type in the lower and upper bounds along with the degrees of freedom. Because this is a greater than problem and we'd be shading to the right, the lower bound is 15.94. We would be shading forever to the right, so you can type in something really big for the upper bound, like 99.99. Degrees of freedom in this problem was equal to 3. And when you paste this and hit Enter, you'll get the same number that we got, 2.68 times 10 to the negative 4th power. Wrap it up. Since the p-value is small, the p-value is less than 0.05, or whatever you decide to use probably for the most part, we are going to reject the null hypothesis. Then we're going to say that there is, because it's a small value, this is a significant event, there is significant evidence. And at this point, you can copy the question. Is there evidence of a positive association? There is significant evidence of a positive association between femur length and humerus length. This addresses the 4 steps of setting up a linear regression t-test. There's an additional problem on your worksheet as well that you should be able to work through on your own at this point. You'll use data from page 184 and answer the question, is there significant evidence of a negative association between wine consumption and heart disease deaths? So think about what a negative association would look like in your hypothesis. Keep that in mind as you're working through that example.